Hi, everyone. Hope you're enjoying the day. Today, we're just going to take a little bit longer or a deeper look at centripetal force and allow you some time to work on the worksheets involving it. Again, quick reminder, you can use any of these formulas listed to find the centripetal acceleration. Which one's the right one? Well, whichever one's most convenient for you. How do you find the net force required to keep an object moving in a circular path? You just take the mass of the object times its centripetal acceleration. Again, remember, and here's the big idea, centripetal force is not a new force. It's just the name that we give the net inward force required to keep an object moving in a circular path. Again, here's it is again. And again, what creates this net inward force? It could be a combination of gravity, normal force, tension, friction, or any of the other forces we may have talked about, magnetic force, electrostatics. It's just the name that we give that net inward force. So here's a couple of quick examples. Here's an example of gravity providing the net inward force that keeps this car moving in a circular path. It's not quite circular. I realize it's parabolic, but it is somewhat there. It is actually accelerating as it moves through this curved path. And I realize its speed's also changing, but the main force is the force of gravity. Same thing with this car here as this goes through the circular path, particularly at this point right here at the bottom. What's providing the net inward force towards the center of this circle? The answer is it's the normal force of the track pushing it up on the car. Without that track, the train would actually go in a straight line, but it's that inward force that actually curves its path. You can also have tension, of course, just like we had in your lab. It was the tension in the string, which was equal in your case to the force of gravity on the hanging mass, that kept the stopper going in the circular path. Same thing with this hammer throw. The hammer here is going a circular path before the throw because of the tension in that steel cable. Cars going around a dirt track, it's that inward force of friction that provides the force that keeps them going in a circular path. In this case, these are actually sort of drifting at the back. It's just barely, in this case, able to keep them going in a circular path. If they went any faster, the force of friction, the maximum force of static friction, would be insufficient, and they would literally slide off the track and not quite follow this tight curve. You can also get a combination of forces. So at the very top of this loop right here, what inward forces are acting on this car right here? Well, besides the normal force of the track pushing down, it's also gravity. So you've got gravity and probably a normal force pushing down here on the track. And so the net inward force, the centripetal force, is due to the sum of these two, the force of gravity and the normal force. So you can have combinations of these if needed. So we're going to spend a little time doing some quick example problems. Again, remember, centripetal force is the net inward force, just equal to the mass of the object undergoing centripetal acceleration times the centripetal acceleration. Problem solving, what we're about to do here, is if you're solving problems with centripetal force or centripetal acceleration, first thing to do, find the centripetal acceleration using one of these four equations. Find the centripetal force by taking the mass times the centripetal acceleration. And then just remember the centripetal force is the net force required to keep it going in a circular path. So again, just remember that's the net force. So take a look at this problem. This is from worksheet 4. It's very, very similar to the problem in worksheet 3, but just in the opposite direction. We'll talk about that in just a moment. In the problem, you've got a 1,200 kilogram car is driving at 43 kilometers per hour through a valley that has a radius of 25 meters. First question, what's the centripetal acceleration? And for that, v squared over r is probably the easiest because we know velocity in that. The only thing is you'll have to convert that to meters per second. So this will be 43,000 meters over 3,600 seconds, number of seconds in 1 hour. And you'll discover that's 11.9 meters per second, roughly, the 3 sig figs. Plugging that in, dividing it by the radius, you'll discover that the centripetal acceleration, the acceleration due to the change in direction of this car, is roughly 5.71 meters per second squared. How do we find the centripetal force? We just need to take this centripetal acceleration times the mass of the car. The mass of the car is 1,200, so if you solve this, you'll discover the centripetal force required to keep this car going in that circular path is roughly 6,850 newtons. What direction is this net force? It has to be pointing upward at this point, towards the center of this circle. So that's why I put a little upward arrow here. So we need a net force of 6,850 newtons acting upward. So what are the forces acting on this car? The obvious one, of course, is the force of gravity. And remember, the force of gravity doesn't change no matter how fast you're going or if you're being accelerated. It's always just, if you're near the surface of the Earth, the mass times 9.81. So in this case, the force of gravity, 11,800 newtons downward. The only other force acting on the car is the normal force acting upward. Now, normally, if we're not undergoing acceleration, the normal force up on top is equal to the force of gravity. But in this case, we need a net upward force of 6,850 newtons to keep this car moving in that circular path. What does that mean? It means the normal force up here acting upward has to be this much larger than the force of gravity. So what's that force going to be? The normal force in this case is going to be 6,850 newtons larger than this force. If you add that up, the normal force in this case is going to be roughly 18,600 newtons. And you might say, whoa, wait a second. If you've got a larger force this way than this way, isn't the car accelerating upward? Yeah, it is. It's that centripetal acceleration acting towards the center. If the car was stationary and had these two forces, it would just accelerate straight up. But because it's moving this way towards the right as it's accelerating upward, it's going to curve its path and follow this road, which is exactly what you would expect. In worksheet 3, you have a car going over the top of a hill. What's going to be true there? You're going to have a net force acting downward. Force of gravity is going to be the same as it was in this case, but in that case, the normal force is going to be smaller than the force of gravity by the amount of the net force required, acting downward. I'll let you figure that one out as you work together, but trust me, it's not that hard. Worksheet 5 has another interesting problem. We have a pilot, and she's flying her plane in an upside-down loop. And the questions are, what forces are acting on the pilot as she does this loop? We're given the radius, we're given the velocity of the plane, and we're given her mass, which is 55 kilograms. Again, remember, what's the steps we always take when we solve these? The first thing to do is figure out the centripetal acceleration. In this case, if you solve it, in this case v squared over r, you need to convert this into meters per second. So again, 235,000 meters over 3,600 seconds gives you a velocity of roughly 65.3 meters per second. So square that over the radius, 350 or 380 meters, gives us a centripetal acceleration of roughly 11.2 meters per second squared. Again, this is the acceleration due to the change in direction of her velocity, not the magnitude. What's the centripetal force or the net inward force that needs to be acting on her? Well, just take her mass times that centripetal acceleration, and you'll discover that you need 617 newtons of net force. What direction does it always act? It always acts towards the center of the circle. Centripetal, remember, center seeking. So in this case, we need a net force of 617 newtons acting downward on her. So first thing we do, of course, draw gravity on her. You'll discover the force of gravity, 55 times 9.81, it gives us 540 newtons. Uh-oh, that's strange. 540 newtons isn't enough to actually keep her going in that circular path. She needs 617. We need, to keep her going in this circular path, we need some additional downward force. And you might say, whoa, wait a second. What kind of downward force could act on her? In this case, it's probably her seat. Her seat is actually pushing downward on her, giving a normal force downward to provide the extra force needed to keep her going in a circular path. And I know it's kind of hard to visualize this. Let me see if I can try to draw something real quick. Might look something like this. So here she is upside down. Maybe I can draw over here. Here's her seat. And she's sitting in her seat upside down at this point, hopefully wearing her seatbelt. Here's her body. Here's her legs. Sorry, really bad drawing upside down. There's her head. And in this case, there are two forces acting downward on her. Force of gravity, of course, just equal to her weight. But that by itself is not sufficient. So we've got the force of gravity acting downward. That's at 540 newtons. And in addition to that, her seat must be pushing down on her as well, with an additional 77 newtons as she's flying her plane. So that the sum of these two gives us the required net downward force that we need. What would she feel like in her plane? Would she feel like she's falling out of her chair? Not at all. Her seat is actually pushing against her, which means she's pushing against her seat. She'd actually be indenting her seat. She could actually ride or do this without her seatbelt on and still be pushed against her seat as she's doing it. Does it sort of make sense? There's a couple of problems on Worksheet 5 that are pretty challenging. I know we'll probably have to go through them when I get back, but give them a shot. Last little piece on this one. We've been talking about centripetal acceleration, which is due to changing direction. That's A sub c. Remember earlier, before this chapter, we've dealt with the tangential component of acceleration, which is due to the changing speed, where you're gaining speed or losing speed, changing the magnitude of your velocity. But it's possible for an object to be going around a path. Say, for example, you've got a car going through a curve here, and it's speeding up as it's heading up. Now we've got tangential acceleration at this instant and centripetal acceleration. How do you find the total acceleration if something's gaining speed and going through a circular path where it's changing direction? The answer is you've got to do a little bit of vector addition. If you add these two vectors, you're going to end up with something like this. I'll draw the centripetal first. Here's the centripetal going this way. And to add vectors that go head to tail, how do you find the resultant in this case? It's going to be this piece right here. This is the net acceleration if you're both changing magnitude and direction. How do you find that? Oh, it's good old Pythagorean theorem. This squared, the tangential acceleration squared, plus this squared has to equal this squared. Or solving it this way, the total acceleration or the net acceleration is simply equal to the square root of the sum of the squares of those two. And this is only time you have to do this is if you have an increase in magnitude or a decrease in magnitude and a change in direction of your velocity at the same time. I think we're done. Yeah, just a quick review. We'll start again with this slide next time. Good luck. Work in small groups. Take a look at worksheets 3, 4, and 5. 3 and 4 you should be able to do, especially that I basically did all the math for worksheet 4. There's some details on it. Worksheet 5 is the one where we get into a little bit more challenging centripetal acceleration situations, but I think together you'll be able to work out most of them. And we'll go through those the next time I see you. Have a great night, and we'll see you very soon. Bye.